As a summary, we're going to describe here both the Hoffenberg-Kohn theorem and the Consum method schematics. Let me remind you that Hoffenberg-Kohn theorems were proposed in 1964. 1 year later, Consum method was published in 1965. And they prescribe a way to solve and to apply that Hoffenberg-Kohn theorem. So first, let's go with the schematics of this Hoffenberg-Kohn theorem. So first, once we specify the interacting electronic system is filling, we are specifying the total Hamiltonian. And once we have the total Hamiltonian, in principle, we could calculate, even though it's extremely difficult to do, we could calculate the eigenstates associated with the Hamiltonian. And of course, we can have, therefore, the ground state wave function. And from this ground state, we can calculate the ground state electronic density of the system. And the Hoffenberg-Kohn theorem here states the following. This ground state electronic density uniquely specifies the external potential, except a constant is not physically relevant. So that electronic density, that ground state electronic density uniquely specifies the external potential. Therefore, that ground state electronic density uniquely specifies the total Hamiltonian. From that, of course, we can get the eigenstates of the Hamiltonian. We can get any property of the system. Therefore, according to the Hoffenberg-Kohn theorem, once we have the ground state electronic density of the system, we can get any other property of the system. So any property of the system can be directly connected with the ground state electronic density. So in principle, we could define a function of the ground state electronic density in order to get any property, not only the ground state properties of the system, any property of the system. Even though here we are centering the analysis on the ground state electronic density, on ground state electronic properties. But there is a step further in order to characterize any other excited property of the system related to the ground state electronic density. So this is the schematics for the Hohenberg-Kohn theorem. But the thing here is that here we don't know how to calculate this one, the ground state electronic density, or the ground state electronic wave function. This is an extraordinarily difficult task because the system we have, it involves many electrons, many interacting electrons, and this is extraordinarily difficult Hamiltonian. This is extraordinarily difficult many-body Hamiltonian. So what can we do? And this is where Consum method enters. So they did the following. They proposed the following ansatz here. So the Konchem approach, the Konchem ansatz, is to replace the original difficult interacting particle Hamiltonian with a different one, which could be solved more easily. So they propose an auxiliary system, and to switch from a difficult system to a more easier to solve system. And this different one is the following. It's a non-interacting particle Hamiltonian, and each particle is moving an effective potential, which we are going to call it the Consum potential. And this system is assumed to have the same density as the true interacting system. So this is the basics of the Consum ansatz. The thing here is they propose to analyze the non-interacting particle system. So, and this could be the schematics for this Consum method. So here on the left we have the previous Consum theorem, And now in the Hoffenberg-Kohn theorem, okay, we have that everything could be determined as a function of the ground state electronic density. So for the same ground state electronic density we have for this real, or for the true system, for the true interacting system, here we are going to define a non-interacting system having the same electronic density. And if we apply the Hohenberg-Kohn theorem, but for the non-interacting system, then according to that, then it's uniquely specified, that ground state electronic density uniquely specifies the external potential that each electron is feeling. Somehow that's the effective potential associated to each electron, and this is what we call the Kohn-Sham potential, because basically in this case, as the system we have, it's a non-interacting one, the Hamiltonian, basically it has the kinetic energy and the effective potential, or the external potential. But in this case, that external potential, we are going to call it the effective potential, which is what we call the Kohn-Sham potential. And once we have that Kohn-Sham potential, we could calculate any eigenstates associated to that Hamiltonian. Of course, we could calculate that eigenstate associated. As this is a non-interacting particle system, the eigenstates are going to be one particle, one electron eigenstates, which and as the Hamiltonian is spin independent in principle, we can spin in two different parts. This is the special dependent part, and they have the spin dependent part. Okay, once we have these one particle wave functions, we can build therefore the Slater determinant of the n particle system in order to anti-symmetrizing these eigenstates. So once we have that Slater determinant, that's going to be the wave function of this non-interacting system, we can build from this one the ground state electronic density. And as in the Hoffenberg-Kohn theorem is saying that any property, either ground state or excited property of the system, is uniquely specified with this ground state electronic density. And as the ground state electronic density of the real system is going to be the same as this non-interacting electronic system, and as this ground state electronic density could be obtained from this Slater determinant, which is derived from the eigenfunctions of this Hamiltonian, then we could say that any property of this real system could be derived as a function of this Slater determinant of the auxiliary system. So what the Consum method says and helps to us is, in order to calculate the ground state of the system, because for that we are not going to solve the real system, the complex real system, we are going to substitute that with an auxiliary system, which is going to be a non-interacting system, and that's going to be much easier to calculate. So we are going to calculate that non-interactive system, and we are going to get the Slater determinants associated with that non-interactive system. And in principle, any property of the real system could be solved, could be derived from these Slater determinants. So the aim here is going to be to get a good approximation for that Kohn-Sham potential in order to have these Slater determinants here.